Hello, welcome to Chapter 5, Section 3. So this is our last section in the Chapter 5 probability chapter. So today we are talking about conditional probability and independence. So first, conditional probability, another formula. So conditional just means like there was a condition involved. So like basically if we're given information already, what's the probability of something else happening? So are symbols in symbols form for math because we are using like this given information. We use this vertical line. It's not a divide symbol or anything. It's just a vertical line to stand for given. So P parentheses A line B would be read as probability of A given B. The formula looks like this. We are looking for the probability of A and B divided by the probability of B. So an easy way for me to remember this is just and over given. Like whatever information you are given, that's what you're dividing by. So and over given. In words, basically you're basically saying if B already happened, what is the probability of A also happening? That's just what we're trying to answer here. Last video we had an example about home ownership and high school graduate. So I'm going to use the same example here, but now we're going to be finding probabilities of conditional probabilities. Okay, so first, out of the examples that we're going to do today, I'm trying to show you like all the different ways you might see the wording. They're similar, but so just so you're aware. So the first one is the most obvious one because right here they give you the word given. So find the probability that a randomly selected member is a high school graduate given they are not a homeowner. So right off the bat, because they use the word given, we know this is going to be a conditional probability problem. So my formula is and over given. So I always start with what's given. Given they are not a homeowner. So I'm going to look at all the people who are not homeowners because these are the only people we care about. If that's what's given to you, we only care about these people, not the total 500 that we had in total. So not a homeowner would be the 160 people. Okay. So already we know what the denominator is going to be of our fraction. Then on top, it's supposed to be the and. So they have to be not a homeowner and a high school graduate. So out of those people, everyone who is not a homeowner, so we said look at the 160 people. So basically in that row of not homeowners, the people who are high school graduates, there's 89 of them. And that would be my probability, 89 over 160. Okay, so let's do another one. If the member was not a high school graduate, what is the probability that they are a homeowner? So here we're saying if the member was not a high school graduate, so this is our given information. They're saying like, you already know this. You already know that they are not a high school graduate. So when we do and over given, what we're given is that they are not a high school graduate. So we're going to look at all the people who are not high school graduates, which would be the 190 people. Okay, and since we're focused on this column of non-high school grads, we're looking for not a high school graduate, but they are a homeowner. What is the probability that they are a homeowner? So that would be the 119. Okay, so 119 over 190 would be our probability. All right, last one. What is the probability that a homeowner is a high school graduate? So this last way of wording things is, my little trick is always to look like after the word probability, who are they talking about? What is the probability that a homeowner? So here we only care about homeowners. So what we're given is that these people are homeowners. And out of all the homeowners, there are 340 of them. Okay, then we're looking at the out of the homeowners who's a high school graduate, so that would be the 221 for the and part, because the 221 people are the high school graduates and homeowners. Okay, that's conditional probabilities. Next, I want to move on to finding probabilities that are slightly more complicated. So here, we're going to start looking at probabilities where multiple actions are taken. This includes like choosing multiple people, rolling the dice twice or more, or flipping a coin 3 times or more, and so on. So there's more different rules for when we're trying to find these probabilities. So because we're talking about multiple events happening now, or multiple actions, then we need to also talk about independent events. So independent events are when one event can occur or happen without changing the probability of the other. So independent means like one doesn't affect the other, or it doesn't affect the probability of the other happening. Mathematically, we can write this as the probability of event A happening would be the same, would be equal as the probability of event A given B happened. So like whether or not B happened, probability of A would still be the same. And so because event B didn't affect event A, they are considered independent events. So this is important because this next rule for finding probabilities depends on whether the events are independent or dependent. So if they are independent events, meaning the two events don't affect each other, to find the probability of A and B happening, so it's just multiplying the probability of A with the probability of B. If they are dependent events, the probability of A and B happening would be the probability of A times the probability of B given A already happened. So again, dependent would mean like one affects the other, which means that if A already happened, then the probability of B would change, and so when we multiply them together, we have to account for that change. Okay, so one thing I want to point out here is that this probability of A and B is different than the probability of A and B that we talked about last video. In last video, when we said probability of A and B, that was when we were only doing one thing at a time, like picking one person, rolling one die, whatever. So when we're dealing with and here, to me, it's kind of more like and then, like the probability of A happening and then B happening. So I like to think of it that way, and so you really have to read into the problem to see like which and are they talking about. Are they just picking one person? Then it would just be the regular and. Is it like they're picking two people? Then it would be and then. Let's do some examples. So let's say we're trying to find the probability of rolling a 3 on a die twice in a row. So because I'm rolling it twice in a row, that means I'm taking two actions. I'm going to roll the die and then roll the die again. So basically I want 3 and then another 3. Well, first of all, let me determine whether my events are independent. Because when I roll a die, are the probabilities of rolling a 3 again going to change when I roll the die again? No, it's not like the die remembers what you rolled the first time. So these are independent events. We can just multiply them together. So probability of A would be us rolling a 3 the first time, which would be 1/6. And then this gets multiplied because I'm doing multiple events. This gets multiplied with the rolling a 3 the second time, which is 1/6 again. So the probability of rolling a 3 on a die twice in a row would be 1 out of 36. Cool. Okay, next example. In Kevin Malone's jar of M&Ms. First of all, if you know what this is in reference to, go ahead and comment down below. There are 46 red M&Ms, 52 blue M&Ms, 29 yellow M&Ms, 29 brown M&Ms, and 35 green M&Ms. He picks one out at random, eats it, then picks out another. What is the probability that he eats a red M&M followed by a blue M&M? First of all, very unlikely in our situation of Kevin only eating one M&M at a time, but that's besides the point. So what is the probability that he eats a red M&M followed by a blue M&M? So again, he's eating multiple M&Ms, so this would be a multiplication rule again, because we've got multiple actions being taken. So now I need to know, does the probability of him eating a red M&M affect the probability of him eating a blue M&M? So first, I mean, when he does the first thing, it doesn't matter whether or not it's independent or not, because when he eats a red M&M, we can just calculate that probability like normal. So in total, there are 191 M&Ms. And he wants to pick a red one first, so there are 46 red ones. Okay, we know we're going to multiply. When he eats it, there are now only 190 M&Ms left. So, because the second probability now, when he tries to eat the blue one, there are less M&Ms to begin with in the jar. then this would make these two events, him eating a red M&M and then eating a blue M&M, these are dependent events, because if he already ate one, the probability changes for the second one because there's one less item in the jar now. Okay, so dependent just means that the second probability is going to change. The denominator is now 190 instead of 191, but really that's all that changes when we're dealing with independent or dependent probabilities, so it's not that bad. Okay, so then out of 190 now, we're looking for blue M&Ms. There are 29 of them. Oh no, blue is 52. Okay, multiplying this together gives me these giant numbers. 2392 over 36290. Okay, I want to do a follow-up to this question, because let's say we wanted him to eat two red M&Ms in a row. So if this was the case, then my first probability of the first red M&M is still the same, 46 out of 191. But then after he eats that first one, now there are only 190 M&Ms left in the jar, because not independent events, so the second probability changes. But also, the second time around, there's also less red M&Ms in the jar now, because he already ate one. So now there's only 45 left. And so when we're dealing with these dependent events, you need to pay attention to like what else changes in the overall scenario. So this time when we multiply this together, we end up with 2070 over 36,290. Okay, next example. Find the probability of flipping a coin 3 times in a row and getting all tails. Okay, so flipping a coin, are these independent events? Well, I don't think a coin remembers what you flipped the first time, so it's not going to affect the next couple flips. So independent, meaning we can just multiply. So you want all tails. So tails and then tails and then tails would be 1/2 for the first tails, 1/2 for the second tails, 1/2 for the third tails, which gives us 1/8. Cool. Fun fact, the probability of flipping a coin 3 times and landing on like anything is still 1/8. Like heads, heads, tails is still 1/8. Tails, tails, heads is still 1/8. Heads, heads, heads is still 1/8. Fun fact. So next, I want to do an example about SpongeBob. You know, why not? So SpongeBob is jellyfishing and usually has a 40% chance of catching a jellyfish each day he goes to jellyfish fields. If SpongeBob catching a jellyfish each day is independent from the next, what is the probability that he catches a jellyfish 4 days in a row? So here, we're already being told that these events are independent. So it says, if SpongeBob catching a jellyfish each day is independent from the next, blah, blah, blah. Once they say independent, or like these events, we can assume these events are independent of each other or whatever. Anytime they mention independence, it usually means you're going to have to multiply probabilities at some point in time in the problem. So this is a huge clue anytime you're looking at a test or on the AP test or anything like that. If they mention independence, multiplying is somewhere in there. Okay, so we know we're going to have to multiply probabilities here using the multiplication rule. If he is jellyfishing 4 days in a row and he wants to catch a jellyfish 4 days in a row, that means on the first day he has to catch a jellyfish, which is a 40% chance. So I'll just multiply that as a 0.4. And he needs this 4 days in a row. So we're doing this 4 times. Okay, so when I multiply that out, I get 0.0256, which is like a 2.56% chance of him catching a jellyfish 4 days in a row. Much less likely, but still possible. Okay, last one. What is the probability that SpongeBob catches at least 1 jellyfish within the 4 days that he goes? So, in reference to the problem we just did. So here, I wanted to point out at least 1. So in our first video for this chapter, we talked about the probability of at least 1. Sorry, not the first video, the second one. So at least 1 means that you just don't want 0 jellyfish, because at least 1 means you're catching 1 or more. So if I don't want 0 jellyfish, then really I can find the probability of 0 and then subtract that from 1, because it's like the complement of catching none. So I like to think of this as the probability of at least 1 is 1 minus none. It rhymes, so it helps me remember stuff. Okay, anyways. So I need to figure out what's the probability of not catching any jellyfish. So if 40% chance of him catching a jellyfish, then it has to be 60% for him to not catch a jellyfish. But he also needs to not catch a jellyfish 4 days in a row in order for me to get none. So I would end up multiplying that 60% 4 times and then subtracting that from 1 in order to figure out like what's at least 1. I end up with 0.8704. So here, 87.04% that he's going to catch at least 1 jellyfish within those 4 days. Not bad. Okay, so as we're calculating probabilities, another really good way to help us visualize what the problem is saying is tree diagrams. So tree diagrams kind of display like what your probabilities are in chronological order. So like if something were to happen and then something else happens, it's a nice way to display it. And it also helps you calculate both our and probabilities, but also conditional probabilities that involve our and probabilities. So like the more complicated problems is a little bit easier to do. So, for example, Mrs. Fernandez hits the snooze button on her alarm clock on 60% of school days. This is very true. It's actually might be more. If she doesn't hit the snooze button, there is a 90% chance that she makes it to school on time. This is good. The other 10% is like if my cat throws up and then I have to clean it up, that'll make me late. Things like that. However, if she hits the snooze button, there is only a 70% chance, a 0.70 probability that she makes it to school on time. On a randomly chosen day, what is the probability that she is late for school? So here, there's a lot of information here. There's a lot of numbers. So the best way to display this would be the tree diagram. This is what it would look like. So in a tree diagram, we always do things in chronological order. We are talking about here hitting the snooze button and then being late for school or not. So the first thing I want to do is to lay out my options for hitting the snooze button. It's either I hit the snooze button or I don't. If you have more items in your sample space, then you would have more branches of your tree diagram. So I hit the snooze button or I don't. And then because I also want to list or use this to help me find probabilities, I also want to list out the probabilities for each thing happening. So it sounds like the first sentence says, I hit the snooze button on my alarm clock 60% of school days. So 0.60 would be the snooze button, which means there's a 40% chance that I don't hit the snooze button. So within each of our like little branches of our tree diagram, it should always add up to 100% because this is our sample space. Okay, so then if she doesn't hit the snooze button, there is a 90% chance that she makes it to school on time. So no snooze button, 90% chance of being on time. So I'm going to draw my branch under the part where it says no snooze button. And then at that point, I'm either on time or I'm late. And they said 90% chance on time, which means that has to be 10% chance of being late. Just had to pause a little bit for these announcements because there's so many. Anyways, so continuing on, then the next part of the question says, if she hits the snooze button, there is a 0.70 probability that she makes it to school on time. So if I hit the snooze button, then I'm either going to be on time or I'm going to be late. And on time probability was 0.70, which means 0.30 probability of being late. Okay, so on a randomly chosen day, what is the probability that she is late for school? So this actually occurs twice. I can be late for school here or here, depending on whether I hit the snooze button or not. But because I have two situations to consider, I have to find the probabilities for each scenario. So for this first one, I hit the snooze button, but then I could still be late. So because these are multiple actions being taken or multiple events happening, I can multiply these together. So 0.60 times the 0.30 would give me an 18% chance of being late if I hit the snooze button. Okay? And then if I don't hit the snooze button, I still might be late. So that chance would be just a 4% chance of being late that way. Okay, so to find the overall probability of me being late, I can add these two situations together. 0.18 plus 0.04, and if you remember back to our addition rule for mutually exclusive events, we can subtract out the probability of 0 for being late by hitting the snooze button and not hitting the snooze button at the same time, because that will never happen. I can't both hit a snooze button and not hit a snooze button at the same time. That doesn't make sense. So the overall probability of me being late is a 22% chance. And the reason why we're adding this is because we have two different scenarios where I might actually be late. So it's like I can be late if I hit the snooze button, or I could be late if I don't hit the snooze button. So because of that or, like in those two different scenarios, I would add those two probabilities together. So another example using the tree diagram, suppose that Ms. Fernandez was late for school today. What is the probability that she hit the snooze button this morning? I was not late today. It's fine. Okay, so here, because they're saying that she was already late for school today, this is information that you already know. So this is a conditional probability because you were given some information already. So really what we're trying to find is the probability that I hit the snooze button given that I was late, because we already told that I was late to school today. So the probability to find that using our conditional probability formula would be the and over given. So the probability that I snoozed and I was late divided by the probability that I was late, because that's what was given. So snooze and late would be the probability 0.60 times 0.30, because that was in my tree diagram, this part here. Following along, I snoozed and then I was late. So that's the snooze and late divided by the probability that I was late. So when I'm late, that could have occurred twice in this scenario with the snooze button and late, and the no snooze button and still late. So that probability we actually found in the last problem, which was the 0.22. Okay, so be careful when you're doing the conditional probabilities, because the probability on the denominator is usually there's like more to it. So from here, doing out the math, I end up with 0.81 repeating, which is pretty much an 81% chance of hitting the snooze button, knowing that I was late that morning. Okay. And so with these tree diagrams, I want to make sure we do a bunch more examples in class, just for us to get used to everything, and then we'll do some practice as well. But thanks for watching. Have a great day.